related one causes botulism. You probably heard of that too. Very severe form of gastroenteritis, which can also be fatal. In that case, it also interferes with transmission of the muscles, but in this case, you get a flaccid paralysis. You just basically paralyze the muscles in a flaccid state. And when it reaches the respiratory muscle again, you die of respiratory paralysis. You normally get that not from the nail, okay, that you step on, or the rake or whatever. You get it from contaminated food. And it's not the potato salad where the flies were crawling across at the picnic. It's canned food. And sometimes home canned food. That food is not properly prepared. You get soil in it, contains the organism, contains the soil on the organism. The spores will germinate.
So that's how the food gets it, is from the soil? If the soil,
if the food is contaminated with the soil, it's not properly prepared, okay, then the organism grow in the canned goods, low oxygen again, because it's an anaerobe. It produces the toxin. The toxin, unfortunately, is colorless and tasteless. So you may consume the food, not realize it's spoiled, and you can end up with botulism. Sometimes it's commercially prepared food. And usually if that happens, of course, they bring it right off the market, because it can be very dangerous. But more common, it's home prepared food, okay? And when you prepare food at home, you should not just boil, okay, but you should basically pressure cook it to elevate the boiling point, because the problem is these spores aren't killed by boiling. Okay.
What are they killed?
But what you can do if you're not sure of the food, okay, is take the food, hopefully out of the presence of the person that you're getting it from, because you may offend them, and boil it for about 20 minutes, hard boil, because that will inactivate the toxin. Yes?
You shouldn't eat canned good food without cooking it. Is that what you're saying?
You what?
You shouldn't eat canned food without cooking it, like vegetables and things?
Well, most canned food is safe, okay, but occasionally you'll get some, they'll say this lot has been contaminated with botulism. They take them off the shelf and return these and so on. If you see a can, though, it's kind of expanded, okay, like it's gas production, that's not a good thing to eat. Probably something growing in there is producing gas, you know, and it could be something that you definitely don't want. Like, I don't even like to buy dented cans, you know, because it could breach the container, but anyway.
So it
Like I
doesn't
said.
produce like that smell that you could...
No, it doesn't. That's unfortunate. You know. It's odorless, colorless, basically. You can't always tell that it's spoiled.
So if you like pick your vegetables out of your garden and wash them real good, you still should boil them?
Well, depending. Yeah, if you're going to home can, it's a good idea to do that.
So just to pick and fix and eat, it's not likely you'll get it.
No.
It's if you're storing it.
Right. Because the organism doesn't grow in high oxygen concentration. So yeah, if you're bringing it into your salad or something like that, it's when you're canning. Because what you're canning is you're putting in an environment where there's very low oxygen. And that can basically stimulate growth of the organism. It's anaerobe. Okay. Anyway, getting back to what I was talking about. Another function of inflammation, like I say, if it can't destroy the organism, it tends to wall it off. What the body wants to do is keep it confined, because a localized infection is much less severe than a systemic or body-wide infection. And then also, of course, to repair or replace the damaged tissue. This is why we have inflammation. And usually that finger bleeds, it stops bleeding, it's sore, it's swollen, it hurts for a while, and then what? Eventually it clears up, okay? The heat dissipates, okay, you get back to normal color, you lose the swelling, and things are fine. It repairs itself. That's inflammation. Again, it's part of the second line of defense. Okay, what brings all this on? Well, what happens is, when you have an infection or tissue damage, you get vasodilation of the smaller arteries feeding blood into that area. We call that vasodilation. It's relaxation of the smooth muscle. Remember we talked about vasoconstriction, the vascular spasm, and hemostasis? This is just the opposite. You get dilation and increases blood flow. Then, this is tied also with increased permeability of the capillaries supplying the tissue. The capillaries constantly leak fluid into the tissues, but with inflammation, they get even leakier. So what they're doing is, of course, bringing in cells, like blood cells, to fight the infection. They're also bringing in clotting factors to wall off the parasite by forming blood clots, and antibodies eventually to fight that infection. So increased blood flow, that's what causes the tissues to become darker, to become swollen, okay, and because they're putting pressure on the pain receptors, it becomes painful. Okay? And the darkness is because you got increased blood flow, and of course, with that you're getting more blood from the core, that elevates the temperature as well. But some of the chemicals involved here are histamine, good old histamine we talked about. Okay, this comes from mast cells. It can also come from basophils and platelets in our blood. Also kinins, prostaglandins, which are hormone-like substances, and so-called leukotrienes that are released. Increased blood flow, increased capillary permeability. And again, it's the vasodilation, okay, that causes more blood. Blood is warmer, that increases the heat, and the redness or darkening of the skin, and then increased capillary permeability, you get the swelling. The fluid is coming out of the blood, more of it's coming out of the blood than tissue spaces. And it puts pressure on those pain receptors, so this is why it's usually it hurts. Any questions on any of this? Now, as I said, the phagocytes, of course, are attracted to the area by chemicals released from the damaged tissue, chemicals released by the metabolism of the parasite that happens to be there, and also chemicals released by the leukocyte or white blood cells that are already there. And once they get there, or to the area, of course, they're being carried by the blood, they undergo what's called margination, which means, fancy way of saying they stick to the blood vessel walls. Then they undergo diaphoresis, which is another fancy term, which means they can squeeze through the little pores between the wall, or the cells that make up the wall of the blood vessel. And usually we're talking about capillaries, which are very familiar to begin with. Okay, so they're attracted by chemotaxis, following the chemical trail. They get to the area, they stick to the walls of the blood vessels of the area, and then they squeeze through those spaces between the cells that make up the blood vessel wall. We're going to talk later about, when we get into blood vessels, different kinds of capillaries. We're talking about also the structure of the blood vessel wall. And often then, of course, associated with the infection, we have pus, this accumulation of the dead cells, dead host cells, also phagocytes, and the bacteria. And then, this is usually then followed by repair. So that's one of the purposes of inflammation. That repair may be very good when you've got basically the stroma supporting connective tissue, parenchymal functioning to produce new cells. Sometimes it's not as good. You get a lot of scar tissue laid out, especially if it's a severe injury. And in this case, of course, it's the fibroblasts of the stroma that are more active. The fibroblasts are producing the fibers that we associate with connective tissue. And scar tissue basically is collagen. A lot of the collagen fibers that are laid down. Any questions about any of this? Okay, so again, this is part of second line defense. We've seen phagocytosis, part of second line defense, engaged by cells called phagocytes. We've seen natural killer cells, which are not phagocytes, but they're special large lymphocytes that kills by releasing toxic chemicals. We've seen inflammation, which again is attempting to wall off or isolate the parasite, keep it from spreading, also putting toxic products it produces, and then to destroy that organism and the toxin it produces, and then to repair the tissues. Also part of second line defense is a body-wide response called fever. And many infections, you know, are associated with an elevated body temperature, which is the fever. The fever is brought on by chemicals that are released. Now the first thing is, to get a fever, or to have a fever, you've got to change the thermostat. You've got to turn the thermostat up, just like in your home, okay? What controls the thermostat? The hypothalamus of the brain. Among other things, the hypothalamus basically controls the body temperature, or sets that thermostat. This has to be altered. That's altered by the release of prostaglandins, which are hormone-like substances. What causes the release of prostaglandins? It's chemicals released by phagocytes. And the chemical is called interleukin-1. Now we're going to talk quite a bit about interleukins. down to make sense. Inter means between, leukin means leukocyte. These are chemicals released by white blood cells. And basically they're for communication, interleukin, to communicate between these leukocytes, interleukins. They're all proteins. When they first identify them, they usually name them according to what they do. Once they work out their amino acid structure, because they're all proteins, then they call them interleukin and assign them a number. Okay, and it's usually in order in which they were discovered. Okay? Now where does interleukin, and what stimulates these phagocytes from interleukin? Chemicals released by the parasite, often a toxin. So the parasite gets into the body, like a bacterium for example, releases toxins, that stimulates the phagocytes to release interleukin 1. Interleukin 1 stimulates the hypothalamus to release the prostaglandins. That causes the hypothalamus to reset the body temperature, which brings about the fever. Okay, so now you reset the thermostat. How does the body bring the temperature up? Several ways. One thing, vasoconstriction. Vasoconstriction means you're contracting smooth muscle and blood vessel walls, and particularly in the skin. What this does, of course, is reduce blood flow through the dermis and the skin. Remember, the epidermis has no blood vessels. And thus, you retain heat. So you're helping to keep more heat in the body. And then, you increase the metabolic rate of cells. When cells are actively metabolizing, of course, they need energy. Where do they get the energy? ATP. How do they form the ATP? By breaking down organic molecules. But when they're breaking down these organic molecules, they generate not only ATP, which is trapping energy they can use, but what? Generate a lot of heat. Heat is given off as a waste product, but it's a form of energy. And then, shivering. Often a fever is preceded by shivering. A person feels cold. The skin may even initially feel cold. Shivering is what? Skeletal muscle contraction, which is why when we're cold, what do? We shiver, because that actually generates heat. This helps to bring up the temperature. So we help to retain the heat by restricting blood flow or reducing blood flow to the skin. We increase the metabolic rate of our cells, which generate more heat. And then we shiver, okay, which generates even more heat, because those muscles, of course, are giving off heat when they break down those organic molecules to make ATP through muscle contraction. As I said, usually the chill is cold skin, and the shivering often precedes a fever. And then eventually it stops as that new thermostat temperature has been reached. Of course, then the body temperature's going up, and eventually the person does feel warm and feverish. And the fever normally remains in place until interleukin 1 is eliminated, or prostaglandin synthesis, which is released by the hypothalamus in response to interleukin 1, has been inhibited. And our typical fever, when you take for fevers over the counter, acetaminophen, for example, that's from active ingredient Tylenol, or aspirin. What they do basically is block prostaglandin synthesis. And in doing so, they help to break the fever. They block prostaglandin synthesis. And that's what basically allows the hypothalamus to reset the thermostat and keep it set up. So then, the thermostat is reset to normal. It's reset to normal. And then, to bring the temperature down, you get basically the opposite thing. You get vasodilation. Now you increase blood flow to the skin. So now you're radiating more heat. The body's losing heat. Get off more. That's cool. And of course, that's also accomplished by the sweating. The sweating, of course, you're dumping sweat on the surface of the skin, mostly water. When that water evaporates, it takes energy in the form of heat. When you take heat from something, you're cool. That's why the sweating serves to cool. And usually when the fever breaks, there's intense sweating to help cool it off. At the same time, you're channeling more blood through the dermis of skin, so you're radiating more heat as well. That helps to bring the temperature down. Okay? And this is basically the crisis, okay? And that fever breaks, and it's associated with the vasodilation and the sweating. And that related temperature starts to fall. But you know, fever can be useful, but also can be very deadly. High fever is damaging because what it does is denatures proteins. Proteins are very susceptible to denaturation. What do I mean by denaturation? Anybody know? Talk about that A&P what? Yes, no?
Yes.
What is it? Not breaking down. Proteins are not just big molecules made up of many amino acids, chains of amino acids, polypeptides, but they got a complex structure. Remember, primary structure, that's what amino acids are present in what sequence. They also have a secondary structure, alpha helix or beta pleated sheet. All proteins have that. Some, you take those chains of amino acids and twist them around one another, that's a tertiary structure. They got 2 or more polypeptide chains, quaternary. Okay? What happens in denaturation is you break the hydrogen bonds that hold a molecule in a particular three-dimensional shape or configuration. The molecule unravels. Okay? It's an enzyme, and many proteins are enzymes, of course. This can render the enzyme non-functional. Why? Because enzymes, to work, have to couple with the substrate at what's called an active site in the the molecule. If you change the shape of the molecule, you change the active site, doesn't fit the substrate, doesn't catalyze the reaction. So you shut down the reaction. Okay? And almost all of our chemical reactions in the body are catalyzed by enzymes. So if you inactivate the enzymes, you shut down the reaction. When they'll go, be so slow, they're useless to us. Okay? So high fever can damage enzymes, denature them, render them non-functional, and basically shut down a lot of what goes on in cells. And it's especially important in cells that are highly metabolically active, like cells, for example. That's why the nervous system is particularly vulnerable to high fever, because it has permanent growth as a result. And especially in children, where the fever can go up very quickly. So really be careful. Okay, we'll stop here. We'll continue this in on tomorrow's lecture. In the meantime, you'll be kind enough to respond to the roll. Those in the afternoon lab, please wait downstairs in the lobby, not outside the classroom. I'll come and get you ready to go. Okay?